All right, so what we're trying to do in this lab, the idea is that the resonance with the sound wave, right? So to do the experiment, I need either open or closed tube. You remember we discussed two different scenarios. If you take a tube, one end, if you close that, and then place the sound source on the close to the open end, then if I change the frequency of the sound source very slowly, then at one point you will hear a resonance. Resonance means there is a background noise always, like humming kind of noise. And then when the resonance happen, that's the place where exactly standing wave happen inside the tube. Then you hear that background noise increases sharply and then decreases back again. And you have that experience, but we did not hear that from the last experiment when you change the frequency of this of the vibrating string. Then you saw that the amplitude of that standing wave increases to a maximum point and decrease, right? That exact maximum point is the resonance point. Now today's experiment, actually you can hear that because we're going to work with the sound wave. You can't really see this standing wave, right? These blue color lines are the standing wave. When that happens, we have to hear the sound because these are now invisible waves, right? Unlike the standing wave, you really see that. Unlike the standing wave on the string vibrator, you really can see because it's a physical string vibrating up and down. But today it's a molecule vibrating, so we can't really see anything. So we can really hear it. Okay, and let's take a look. What are the two scenarios? So the case number one, if I take the tube and if I change, for example, if I fix the frequency of the source, then I can slowly change the length of the tube actually, right? We can do this experiment two different way. I can either change the length or I can change the frequency. Okay, both can be done. So if I change the length slowly, first time when you hear the resonance inside the tube, possibly standing wave should be look like that, because close end always should be a node. The reason close end atoms or the molecules doesn't have freedom of vibration because that is close to the exact this wall, right? So it cannot vibrate. Because of that, it should be always a node. However, in the open end, always should be anti-node because the atoms or the molecule here in this area can actually vibrate as free as possible, because it's completely open for both sides. So if you put the source here like the speaker, if you do this in class, it's going to be a speaker, then actually this particle right here, the molecule right here, can actually vibrate much faster, as free as possible. But when it comes to here, vibration should be almost zero, vibration amplitude. So if I get that condition fixed, this side is node, this side is anti-node, possible first resonance should occur when you have a lambda by 4 amount of wavelength inside this tube. So if I use that with the tube length L, lambda by 4 equal L, but I can have different modes, because if I change the length or change the frequency, I can have different resonance mode. Now the second resonance mode should be, this place should be always a node, and the second opening can be, first opening was here, right? Lambda by 4, then the second one going to be somewhere here, that is lambda by 3. And the next one is lambda by 4, and then so on. So that means 5 lambda by 4, and then so on. So which means if I write it down this as a series, this we done actually this in class. Okay, you can refer that as needed. If you done as a series, then this n should be always a odd number. So that's the only difference for this one. The other option going to be very similar to the string vibrator scenario. So which means technically the lambda can be 4L divided by n. N should be the resonance mode in this case. Okay. Question? Okay. Then which means you know the standard wave equation always I can use the speed equation, right? Wave speed is V equal lambda f. If I combine this equation with this one, lambda is 4L over N and times Fn, and the V is actually speed of the sound. If I'm not changing anything, you remember in class we discussed the speed of the sound can depending on various things, right? For example, it can depending on temperature. It can depending on bulk modulus of the medium. If you have a different air, then the sound speed is actually different. And if you have air density different, that can be the affecting too. But in this experiment, when you do the experiment, we're not going to do any of those changes. The temperature going to be fixed. The properties of the air are going to be fixed. Because of that, the sound speed going to be a fixed number. Because of that, simply we can say now, if I rearrange this formula, write here equation number 2, frequency of the resonance mode is actually NV over L. This part is a constant times the L. So I can do an experiment either by keeping L, N versus Fn, or I can change the I can keep the N, I can change the L versus Fn, and then so on. I can do different variables according to our need. And then by doing such experiment, we can, for example, calculate the speed of the sound. That's what actually planned for this this lab. Question. Okay. Then let's continue and then start the experiment. This is actually open tube, the next part. Both ends are open, but unfortunately the simulator can't actually do this part. But if we do this lab in class setting, actually we have a setup. We can do actually both. We can do open tube and the closed tube, both of them. Only difference is that this formula, you can see the series equation for lambda are going to be different, because if both ends are open, if you place a source right here like the speaker, this open end should be always acting as antinode, because the air molecule can vibrate as free as possible, right? In between can be anything, like the standing wave you observed last experiment. Because of that, if I keep that condition fixed, both ends are antinode, then which means the first resonance can occur only up to this condition. So this is actually lambda by 2. And then complete lambda, and then complete 2 lambda, and then so on. So which means in this case, n going to be all the numbers, 1, 2, 3, 4, all the numbers. This equation is exactly similar to the equation we use for the last experiment. There's no much difference at all, except last experiment velocity we could write force of tension divided by the mu mass density. So that's the only difference. Otherwise, it's going to be looks exactly the same. And we're not going to do in open end tube, because our simulator can actually simulate only the closed end. So we're going to be doing closed end tube experiment today. Okay. Let's go to the simulator page, and then you can click on this link right here. That should open up this page. Okay, everybody have it? Anybody have any problem, question? Okay, seems to be there's no problems. So let's continue. Now let's take a look what this simulator have. A couple of options on your left hand side. You can see we can select the surrounding air, so we can change that. Different type of mediums, just normal air, like our background, the collection of all the different type of air. Or I can select carbon dioxide, specific type of, or nitrogen, oxygen, argon, or chlorine. So we don't need to do all of these. At least we'll try to do maybe by changing a couple of them at the very end of the lab to see the effect of the type of the air. Okay. And the second option, you can select the surrounding temperature that we're going to check later in the first part of the experiment. We'll fix this into the room temperature. So we can test actually whether the sound speed is really changing as a function of temperature or not. This experiment, we done that calculation in class, okay? So we can really check that. And tube diameter, actually there's an error correction with the tube diameter. If you have a larger tube diameter, there are going to be a little bit of error, but we don't need to do that error correction with the smallest tube diameter. Like this is 5 centimeters, so we'll do without error correction with the tube diameter. That's okay, I think. We're going to see a little bit of error, but that's fine. Tuning fork frequency, that is actually the source, right? You see on the top, the tuning fork. So I mentioned this couple of times in the class. Tuning fork is just an item, has a 2 metal bar like that connecting together. And then usually there's a like wood handle here, right? You take the tuning fork and then slowly give a small force to one of this side of the tuning fork, usually by using a hard rubber piece, because we have to be very careful. If you hit the tuning fork very high force, then the frequency can change. Then the tuning fork vibrate up and down here. As a result of that close by air molecule vibrate up and down, now the wave gonna go in, and then you can see how the setup is look like. You have a water tube right here, and then inside that there's another tube, right? So if you take a look what is really happening, this part you can bring it up and down, right? See that? So which means if I bring this up and down, this inner tube is actually acting like a closed end tube. One end is closed with the water layer, other end is open to the air. So that's how we're gonna do this experiment really, okay? So we have a closed end tube. So after we give the vibration, we're gonna slowly bring this up and then try to find the first resonance mode. Let's do a quick test. So leave everything as it is, temperature and everything, nothing much to worry there. The frequency also leave it as the closest. Then all we have to do, you have to click this sound on, because if you click that sound on now, I can't really see the wave inside, right? Unlike the last experiment. So I have to really hear the resonance point, right? So click that on. Then when the resonance happen, you will actually hear a sharp noise, okay? That's where the resonance happen. Now all we have to do, click on the results too, that actually tells you what to expect. And then slowly bring this up. We need to hit the tuning fork, sorry. So you have to hit the tuning fork, and then you can see that wave now, right? See that? Tuning fork is vibrating. See, the tuning fork is vibrating. That vibrating create the wave, but in reality, you can't see this wave, right? So now you need to slowly bring it up. You hear that noise? See that? So whenever the resonance happen, you actually hear that noise. Okay. Okay, so that's all. It's actually very simple experiment. So all you have to do every time, we're going to change the frequency, and then we're going to change the temperature later, and then so on. So the ultimate goal is first to figure out the sound speed. So that's the plan. It is very straightforward and easy here, because you hear that noise very clearly, right? See that? That's the resonance point. But the problem with the in-class setting, you're not going to hear that such high intense sound. So it's going to be very, very weak sound. And then there's a background noise too. If we do this in class, then we have to be very careful. We have to really bring our ear as close as possible here. And then one person has to do it, because if the person change, then the sensitivity change. Then if one person take the one measurement and the other person take in the other measurement, then the position you're measuring and the length of the tube you're measuring can be changed actually. Because of that, one person has to hear and then other person has to slowly move this. When the person hearing feel that is the right place, then you read what is the length of this tube. What we need is the length of this part, right? That's all really. So it's very, very simple experiment. This exact setup we have in our lab too. This exact setup this way. We're going to do, if you're doing this part, exactly the same way. There's no difference at all. There's a water container and the inner tube. Tuning fork. Only problem with our setup is this setup particularly very, very old, and tuning fork has wrong frequency, and this tube's actually not in good shape to use at all. So that's the problem. We have a new setup with the electronic gadget. So that is the one we're using, hopefully from next semester. Okay, question. All right, then let's go and take a look lab manual little bit. The part one, what we're trying to do is speed of the sound with closed tube with the first resonance. Right now you see there can be a different resonance, right? Let's take a look. Can I get the second resonance with the 300, right? So after you hear the first resonance, if you continuously increase the length, you can see that resonance now disappear, right? So you continuously increase this length more and more to upward direction. Continuously bring it down. First resonance, and then we'll continuously go up and then see whether I can get the second resonance. Okay. More. See, now actually tube B is much longer, inner tube, right? So that's the second resonance. So you go more and higher. So I can't reach the third resonance because there's no any length I can move this more, right? So this is about usually 1 meter length tube. So usually we can get at least 1 or 2 resonance more. That's it really. But if you remember the last experiment with the string vibrator, you can get like number of nodes inside the on the standing wave, like maybe sometime we got like about 10 loops or even more. So that freedom we don't have here. We can go only 1 or maximum 2 resonance mode. Okay, question. No questions? Okay, then let's continue. And now you know what we really like to see, like to measure here the length when the resonance happen, right? Let me show you how to measure that too. When the resonance happen, the sound is very loud. You can actually switch off the sound for the moment. Then to measure exact location, you see that a little bit difficult to see that. There's a tape attached. So all you have to do, click on this icon and then make it zoom in. And then you can measure exact this line right here, 25, 25.5, 25 point about 7, right? This is a regular meter stick tape, okay? Centimeter, millimeter scale. So I can measure exact length right here. Usually there's a meniscus, you know, and if I have a water tube, we have to measure exactly the lower level of the meniscus and things like that. But those are not important in this case because this gives the most correct, accurate reading here. Okay. All right, question. Okay, then let's continue. Our table number 1, what we're going to do, we're going to change the frequency of the tuning fork, and then we're going to measure the length of first resonance mode. Okay, length of the first resonance mode. Then by using the length, you know how to calculate the lambda, right? Because you know lambda is equal 4L over n, and then n going to be 1 now. Okay, we're doing only first resonance mode. We'll calculate lambda. Then we'll calculate 1 over lambda because we're interested to measure the speed of the sound, right? So which means technically I can say speed of the sound is equal 4L times the Fn. We can actually even escape this 1 over lambda, doesn't matter, but that is easier if you have it. The reason, you know, if I'm using this equation, V equal lambda times f equal lambda times f, then I can make a graph f versus 1 over lambda. If you make a graph f versus 1 over lambda, frequency versus 1 over lambda, then you can see slope of that graph gonna be actually velocity, okay? Which means that graph gonna be linear. Slope of the graph gonna be speed of the sound. So that's why actually there's a column, it's separately telling you make that column. That is easy when you do the graph. Then I can make a graph f versus 1 over lambda, these two columns, and then I can get the slope. That slope should be equal to the speed of the sound. That sound is speed, you can actually expected value you can find on the simulator. That's usually about like 331. 331 at 0 degree, you know, we have to do the temperature correction. So if I get this number directly from here, that will be done automatically, the temperature correction with this one. Okay, this is very close to 0 degrees Celsius. Let's take a look the number. See, that is about 332. At 0 degree, it's about 331. Okay, correction. All right, then let's take the reading. So let's start from 300, and then let's keep all of these are constant. Don't change that at all. Okay, keep it surrounding temperature to tube diameter. Let's see whether I make any difference there. Let's do at room temperature first part, and then everything else you can keep it as the lowest position. Okay. Yeah. Only room temperature means about like 25 degrees C roughly. Okay, so only 25 temperature to reach the room temperature there, but the diameter and then frequency start with lowest value. All right, so the frequency gonna be in units hertz. Length we are measuring, I need unit meters. We can measure directly in centimeter, but we need the unit meter, okay? Then I can find the wavelength. Wavelength gonna be in unit of meters, and then 1 over lambda, that's gonna be 1 over meters, and then sound speed at the end, you should get the unit of meter per second. First frequency 300. Now, I mean, technically, I can't read anything more than 300. You know, there's no decimal place or anything. But for the accuracy of our calculation, let's write it down this number this way, okay? Otherwise, it's going to be only one decimal place, the only one significant figure. Our calculated value may not be really show some accuracy, okay? Because of that, you can format these cells, all of these cells. You know how to do it on the Excel. Highlight it, right click, format cell, numbers. Let's use at least one decimal place than what it show in our simulator, okay? Because then we have about 4 significant figures. Then when we do the calculation, we can have a little bit of high accuracy. Otherwise, if I write it this as a 300, then I have one sig figs. My calculated value going to be not showing really any accuracy at all. Okay, that's why. All right, guys, so let's measure now all set up. I think it's better to include the temperature here too. So you can include the temperature here, maybe on the top of that table. That may be useful. Otherwise, we don't know which temperature we done that calculation, right? So I would suggest include the temperature here. We are using temperature is about 25 C, okay? Okay, following, any question?
Professor?
Yeah.
Can you show me how to show the decimal places again?
Oh, you just need to format this one. Just highlight this whole part and then right click. To highlight, you just click and drag, okay? And then right click, format cells. and then number on the very top, number again here, and then change these decimal places to 1, then click OK.
All right, thank you.
Yep. Anyone else has any question? No problems. Okay, then let's collect the data. So all we have to do, you have to click the switch on button here for the sound, right? Otherwise, no, you're not going to hear anything, right? Click sound on, and then slowly increase the length of this inner tube by bringing up. When you hear the vibration, when you get the maximum intensity, just stop there, okay? And then sound is really, too intense, so you can switch off the sound for the moment, but don't change the length. Then click on the zoom in button. Then you can measure the length exactly, okay? Now the length should be 28 centimeters, 28.2. This is a meter ruler. 28.2. If you go to meter ruler, meter ruler least count. Meter ruler least count is 1 millimeter. Because of that uncertainty of the meter ruler, going to be 0.5 millimeters, right? So which means technically, if you're using or measuring anything with the meter ruler, in physics 1, you discuss this thing very in detail. If you're using anything with the meter ruler, you have to show that accuracy, right? So which means that in terms of meters, I can go 3 decimal places, that is the least count. I can actually add one more 0, 4 decimal place, okay, to show the accuracy, which means I'm measuring here 28.2, but I need the meters, right, which means 0.282. But I can add another 0 because that's the accuracy, okay? But you have to show that, which means all of these, right click, highlight, right click, and the reformat to show 4 decimal places. Then we are showing the right decimal places to the accuracy of the meter ruler. And then this also has the 4 significant figures. Then our calculated values actually later, we can go for 6 feet totally, okay? So that's much easier. All right, question. No problem. Okay, then all we have to do, continue. So let's do the calculation to check whether we're getting exact numbers, okay? We may have to include that the length correction, because there's a small length correction we have to consider when we measuring this. Let me show you that. So let's try without that to see how much error we occurring. If you zoom this in, you can see now the tuning fork is a little bit above, right? Because of that, when we measuring this wavelength, you can see it can go a little bit above actually than the end point of the tube. So which mean we may need to consider that length correction little bit above, not much. Okay, we have to do experiment to figure out how much length correction is happening. So in this simulator, they actually give you the length correction, I think, how much length correction we should consider. If you click on the show results, then they will telling you that end correction, consider 1.5 centimeter. Let's calculate without that to see how much error we're getting. If the error is very small, nothing much to worry about it, we can just continue without that. If the error is fairly large, then we can consider that length incorrection too, okay? Which means the idea is that unlike that your last experiment, we can really visually see the endpoint, right? Because it's a physical object vibrating up and down, but now you can't really visually see that endpoints, right? Whereas this exact endpoint of the vibration molecules, we don't really see that. We basically assuming that is exactly right here, but it may be little bit beyond that. Okay. Let's do this calculation for first one. Lambda, you know, you can go back to page number 1 and then take a look. Lambda is 4L over n. So which means I can basically do 4 times equal 4 times the length of the tube. So I get the lambda. That's good for significant figures, right? And then we can do 1 over lambda equal 1 divided by lambda calculated. Since that is the calculation in the middle, you can have little bit of more decimal places. That's okay, because that is not our end calculation. Anywhere in between the calculation, you can have it. Otherwise, round it that to 4 significant figures. There's no meaning having more than 4, right? So let's do 4 sig figs. And let's calculate the V. So V is F times lambda, right? So let's do that. So F 300 times lambda. So I get 338. So now you can see this is at 25 degrees, right? I have to find it, right? Correct one. Let's do the temperature correction. You remember the temperature correction we have to do? So let me write it down, that temperature correction. Lambda is just 4 times L. 4 times L. Okay. And then V is lambda times F. You can insert the symbols and everything here nicely if you want the lambda here. Lambda times F. Okay. So let's take a look now. Let's do the temperature correction first, okay, to see what we getting for the velocity, whether it is reasonable or not. How to do the temperature correction for the speed of the sound? Equal sign. Sound speed at 0 about 331, right? Times, and then square root SQRT parentheses. Then I need the temperature, this temperature in Kelvin, right? So which means another parenthesis 273 plus 25, because this is at 25 degrees C, divide by 273. That's our temperature correction equation, close bracket, hit enter. Now you can see I should expect about like 345. So it's fairly large difference, okay? Now, if you do this in class, that difference is very, very normal. You're not going to get exact number anyway. But let's take a look what's the answer they have on the simulator. If you go show results, that will actually tell you the results. So we should expect about like 346. So which means if I do the end correction, I should maybe able to get a very low percentage difference. Let's try that. Right, let's do the percentage difference with the temperature correction at the end correction, right? So which means the L should be the number we measured plus 1.5. Let's try with that. .015 centimeters, sorry, 0.0150. 4 times L C13, 1 over lambda, not much difference. Difference is still about the same and even larger, I think. We should go with that without end correction. I don't know how they're getting 346. That's very close to what we get here. But it seems to be we're not going to get that number at all in our calculation. Yeah. Let me check that length again. 28.2. All looks good. 28.2, and correction is 0.015. That looks good. 4 times L, 1 over lambda. Instead, actually, we'll go without the n correction. That's okay. So let's do the percentage difference to see how much is the error. Okay, let's try percentage error here. TBS parentheses expected value minus calculated value divide by expected value multiply by 100. There we are close enough. Percentage error is about 2.2%. So we are in the margin. That's good. So we don't need to worry about that in correction. But don't read their number at all, okay? So we don't need that. Just we need to do the experiment as we usually do in class setting, okay? Everybody get that idea? Everybody okay? Any question? I just checked that all of them to make sure we are doing here everything correctly, okay? That's why.
Can I just see the equation for the last part?
This one or this one? Temperature correction?
No, the other one. The one
This
under.
one?
Yeah.
That is percentage error. Let me write it down that also. Okay. Wait, let me write it down that equation here, okay? Temperature correction equation we use actually in class some time ago, okay? This is V expected. I will write V parentheses expected value, or you can say standard value, and then this is percentage error with that, okay? And the equation for the temperature correction, let me copy paste that. This is that formula. We used that in class setting some time ago. So you can refer that as needed, okay? Okay, so that is the equation I use. That's the equation I use. Let me highlight that part, and then this is percentage error. Let us copy paste that also to here. Then you can refer that as needed. All right, so that's the equation for the percentage error. All of this part which I done just to make sure everything we do is actually correct, okay? So all the numbers and everything which I observing is correct. So that's what I want to check first before I do the experiment. Good question? Okay, now you can continue with the experiment, right? So now it's very simple idea. Now let's continue. All we have to do what? Change the frequency, measure the length, but we are interested only first resonance, okay? First resonance mode. And then you can include actually this information when you do the discussion part. You can say when in your discussion and conclusion part, you have to discuss one small paragraph for every table. So what you've done, how you've done the calculation. It's better to include a little bit of information about the Excel too, because now we're doing all Excel function. We don't really, I would advise you not to use the calculator, instead do all the Excel function. That's a good practice to have. I think most of you know how to use Excel anyway, but the idea is that stick to the Excel calculation instead of calculator, okay? That's all. Rest of this table is extremely simple. Now all we have to do what? We'll change the frequency. Change the frequency by maybe, let's see how many data point I need. 1, 2, 3, 4, 5, 6. How much I can go? Let's go each 50. If you go each 50, I can easily go, I think, six or more data points. Yeah, let's go 50 by 50, okay? All you have to do, click this icon and then slider, slowly slide. until you reach 50. If you can't reach 50 exactly, you can use the arrows on your keyboard, okay? Right hand side, 2 arrows. So just click on this blue icon, then it's highlighted, then use the arrows, then you can slowly increase. Then click the sound on, and then let's do the experiment again. Okay, now I'm on 350, right? Then slowly increase. You have to find exactly maximum point, okay? When the maximum resonance happen, stop there. I think we'll get rid of the sound first because it's too much strong noise, right? Then click on the zoom in and then measure the length accuracy. Actually, length is here, it's showing, but don't read that directly. Instead, try to get it as accurate as possible here, okay? Now it is about 22.5. So which means now I am on 350. Now this is 0.2250. And then rest of the calculation now very extremely easy. You know, in the Excel, if you do one calculation, the rest will do automatically for you. All you have to do, click all of these and then drag downward. And then one click, it will do everything for you automatically, okay? I can even click this and then highlight all of these. I can represent 4 significant figures. And here I can represent 4 significant figures. And here also I can represent 4 significant figures. Okay, that's why in the beginning I purposely brought it this frequency this way, then our accuracy is much better. Okay. Question. Okay, good. So I want to check this one with that temperature, with that end correction, whether we're getting the good number now. And 0.015. Yeah, actually that end correction is much strong as you go downward direction, okay? Because if you measure the length, when your measured length right here getting more and more smaller, then your error actually much higher. So I would suggest we'll use that end correction for all the rest of the calculation. That seems to be very important. So you can write it down here, end correction. Let's add maybe into here, okay, end correction. End correction is equal 1.5 centimeters, okay. Just add that to. PE, maybe it is something useful to check. Actually, in the lab manual, I did not ask you to do that for every single measurement. Instead, what we're going to do, we're going to actually make a graph, and then by using graph, we're going to check that really. So we don't need to check the percentage error for every case. So the idea is that take the velocity by using the graph because that's going to be more accurate value. Okay. I would suggest don't need to calculate that for each, but you know now what the number we expecting. And then if the number is too much off, then we can do a little bit of correction with the end correction value. Okay. So we are in fairly decent margin in terms of PE. So it's still about like less than 5%, that good amount of percentage error. Okay, let's continue then. So the plan of the experiment is actually make the graph and then get the sound speed by using the graph. Okay, let's see whether the graph will give us a better value. Okay, question.
Isn't the end correction in millimeters?
Say it again.
End correction, isn't it in millimeters?
Is it in millimeters?
Yeah. Oh, never mind.
No, it's in centimeters.
All right, thank you.
Yeah. It's 1.5 centimeters. Okay. All right. So now let's continue. Next one is keep the sound off. And then whenever you want to take the reading, then click this, because otherwise it's going to resonate in continuously. Okay. The too much strong noise. Next one, we need about 400, right? 400, make the sound on, and now you can maybe bring it back all the way down and then bring it up slowly. Okay, so when you feel the maximum intensity there, then stop and then make the sound off, and then you can read the number here, the length actually, but instead we'll measure it as we do in class setting by using the meter ruler. 19.4. Okay, so now we are on 400. 19.4 mean 0.1940, right? And in this calculation, it will automatically do, we should do the end correction. End correction means this L value has to correct with 1.5. Okay, so I have to add that, which means like for the previous one, if you want to add anything, always make sure you put the equal sign in front and then plus. I'm on unit of meters, right? Because of that 1.5 mean 0.015. 0.015, okay, 0.015 in centimeter, in meter scale. Okay, now you can see, because the sound speed what we expecting is actually about the same number, right? That should not change as a function of my frequency change, right? Because frequency and length is changing, but the sound speed, we discussed that earlier, should not change at all. We expecting it to be about the same number. You can see it's behave about the same, but not exactly constant, slightly changing. That's our experimental error. That's totally okay. Okay, so that's all. Then we'll do 450, then 500, then 550. That's good enough. Then let's do 450. Anybody have any question? 450. And then I should go back to the simulator. I'm going to bring this back all the way down and then click the sound on and then slowly increase this. Okay, when you hear the noise, we'll make the sound goes away and then observe the tube length, inner tube length, 18.1, 0.181, and then increase this to 500, right? 500. And then go back to the tube, bring it all the way down, click the sound on, and then slowly increase this. Oops. Yep. Okay. 15.6, 0.156, and then last data point we need 550. 550, and go back and then bring it back again up. Oh, sound is off. Okay, so that number is about 13.1. 0.131, and then to do this calculation, all you have to do, If you want to do, you can do one by one, or you can highlight all these 3 columns and then click downward direction. That will do the calculation automatically. Only thing I have to take care of now, that correction, right? You see that correction I did only up to there. So let's do that correction. So which means the next one also I have to correct it. Equal sign plus 0.015. And then this one also I need to correct it. Equal sign plus 0.015. And equal sign plus 0.015. Okay, so some numbers are much off, some numbers are a little bit higher, some numbers are a little bit lower. If you take the average, we will get fairly decent value, what we very close to what we expected. Okay, question. All right, then let's do a graph. You remember earlier we discussed, I can make a graph f versus 1 over lambda. So that means these 2 columns. So let's make a graph f versus 1 over lambda. You know, we discussed that I think during the last class. There's a couple of different ways you can make graph, but the method I would like to do is that make the empty graph sheet and then add the data. Okay, so click elsewhere, outside the table, then insert. In the middle of that you see charts. Always you remember we do only scatter plot. Okay, scatter plot, and then double click on the graph sheet. Then you will see data selector. Then click on that, add. Then we'll select the x values. X values in this case we interested to do a graph f versus 1 over lambda. So x value should be 1 over lambda, and then y should be frequency f. And click OK. Click OK again. Then I should get a linear graph, fairly linear, 1 or 2 point goes off. That's very normal. And then we'll fit the data. I need the trend line. So usually all of those options are here. Left hand side, very top, chart element, axis title. We need all the axis title, and we need the trend line. We need trend line linear. Okay. Let's format this to a little bit. Chart title, you need to have a chart title here. This is going to be frequency versus frequency versus 1 over or inverse lambda, you can say, or 1 over wavelength. One over wavelength, and then this one gonna be 1 over wavelength, x-axis. Usually we don't write just a letter here. We don't write 1 over lambda. Generally for the topic also, the graph, you don't just write f versus 1 over lambda. Instead, you have to type that whole term, okay? And unit's gonna be 1 over wavelength, mean 1 over meters. And this one gonna be frequency. We don't just type f, right? You have to type the whole word, frequency. And the unit should be hertz. Hertz 1 Hz. Okay. Then my trend line is there, best fit line. I need to get the slope. All you have to do, double click on the trend line. Then the trend line formatting appear, your right hand side, very corner. Last icon here. Yeah, I think we did not do the end correction for the 300. You can do that actually. I think everything else I did the end correction. Probably I did not do for the first one. Yeah, we can do that actually. 0.015. Yeah, then if I get the average, there's two numbers higher, two numbers lower, we will get a fairly close value to the expected number. Okay, so double click on the trend line and the trend line options, and then all the way down here, I need to click all three because we expecting intercept to be 0. And if you want, you can extrapolate the backward direction because it should go through 0, 0 point to see that, okay? But it's not really super important, okay? And the number which I'm getting from the number which I get from the graph is about 336.9. Close enough, and you can see R square is fairly good. We have about 0.9987. Not the perfect. You can see two data points are actually going much further off from the base fit line, right? So which means we expecting it to be slightly off from the one, right? Comparing to this is like a real life experiment scenario. We should not get the perfect reading, right? In real experiment, that's a good simulation. You actually not getting the real experiment, real perfect data set. That's good. Okay, question. Then all we need to do is compare the number you're getting from the graph to the average value you get from here. Okay, let's do the average. VAVG. VAVG, you can calculate here, equal sign. You know how to do the average function. Equal sign, average function, take the average of all this. And I'm getting 340.5 meter per second in unit. And the expected value 345. Let's do the percentage error between average and the expected and the graph value and the expected. Okay, I think all of those are asking on your lab manual. Okay, you have to answer all of those questions at the very end. Let's see what's the question it asking. Go into the table right here. On the table, you see it asking a couple of different questions. So it asking calculate the average and then do the graph, find the V from the graph. Then it asking you to do the temperature correction. We just done that, okay? This equation right here is written for Celsius, okay? Be careful when you're doing that. That's not the equation we like to use. The other one with the Kelvin, but you will get about the same number. Then it asking you to do percentage error with the average you get from the table with the expected value and the V you get from the graph and the expected value. Okay, let's do that, both of them here. So let's do PE, and then I'm going to do here V average, VAVG versus V expected. Okay, let's calculate that here. Equal sign, ABS, parentheses, V average 340, expected value 345, right? 345 minus 340, divide by 345, multiply by 100. So it's fairly very good number. And then let's do the same thing, same calculation, PE, but now let's do V from the graph versus V expected. And let's take a look what number we get from there. Same kind of calculation, right? Equal sign, ABS, parentheses, we expected 345.82 minus sign. And from the graph, we get in 336.9. 336.9, close brackets, divide by expected value, multiply by 100, 2.5. Still fairly decent value. Okay, question. All of these calculation you have to include in your discussion section, okay? Because now you have to be careful in the procedure. These questions are not given. Instead of that, I wrote those questions just under the graph or under the table number 1. Okay. Each table has a certain amount of questions, so you have to answer all of them. Question. Okay, no problem. Yeah, you can add, since if you're using the Excel in your discussion section, you can directly add this function really. Now you don't need to really type everything. If you're using the Excel when you discuss this part about the table number 1, right? Then you can say, Excel, I use this function to calculate this and then so on. That is actually much easier. Okay. Good. Any other question? All right, then let's take a look the second one. So that some of these letters are hiding there. Let me copy paste into this. You have to really take care of this, some of this before you copy paste this table into your lab report. Take a look whether everything is properly adjusted and then everything is showing properly and then so on. Because you can see some of this table heading, some of the letters are hidden here because it's too lengthy, okay? All right, so let's take a look the second part B of the experiment. Everybody okay? Any question? Part B of the experiment, it technically nothing new. Only thing is that the exactly same experiment, but we're gonna take a look now, second resonance, okay? See the topic? So now we interested second resonance, okay? So the first one we this for the first resonance. Okay, that is for the first resonance, then you can see it clearly, I think. And now we are doing it for the second resonance, okay? Okay, for the second resonance. Question. And this one also we need that information, right? Temperature and the end correction. So it's better you include that information here. So that's going to be about the same. We're going to do same temperature, same end correction. There's nothing new. It will be about the same, okay? So make sure you included that information from here. Okay. I add one small line here and the one row and then included that information. Okay, let's do for the room temperature like we done earlier. Any question? Let's add all the units, otherwise sometime later you might forget the units. To merge the cell, all you have to do, highlight the area, any area you want to merge. Then on the top, you will see an icon right here. In alignment section right here, you will see a merge cell. If that is not visible, you will see an up down arrow. Then click on that arrow, then you will see the merge and center. Okay, so let's add the units 2 before we start the table. Length is in meters, because of that lambda going to be in meters, 1 over lambda going to be 1 over meters, and the V going to be meter per second. There's no difference at all. It exactly previous calculation. Everything is same. You can add those equations. 2 lambda is equal 4 times L, and then 1 over lambda is fine. V is equal lambda F. Those equation you can add as needed. Okay. All right, so to do that, only thing I have to make sure I observing second resonance. That's the only difference. Now let's see, let's go back to frequency 300 and the keep everything as it is. Tube diameter is time, the room temperature is fine, the surrounding is just air. Don't do any changes there. Okay. Let's bring this tube back all the way to minimum length point, and then let's see, switch on the vibration right here. Sound should be on, and then let's bring this up slowly to see whether I can get the second resonance. That means I should hear first that high noise, and then it should disappear, and then it should appear again. Okay, so that's what we're observing. Let's see whether we can get that. So that's the first one. So you have to continuously move up so it disappear. Now after some time I should be able to get that. Go more up, more up. That's the second one. See that? After if you bring more up, then you can see second also disappear, but there's no enough length to go to the third one, right? So only second one we can go. So let's bring this back. When you hear maximum noise, let's get rid of the sound and then click on this button. Now you can see second resonance happen about like 81.3 centimeter location, right? So that's why this experiment we can't do as a function of resonance mode. Last experiment, mostly we done all the calculation by changing in, because we can get many number of loops inside, in between vibrating section of that string. But this we can't do it because it's too lengthy. And if it is a real apparatus, you can't really have this tube more than 1 meter length. And it's difficult to handle too. These are glass tube, and simple mistake, you're going to break the whole item. Okay, question. Frequency 300, length is 81.3, mean dot, I need in meters, right? Dot 8. Go back and take a look, 813. And then I need to have 4 significant figures, right? For the frequency column. Let's format that. At least 1 decimal place, show you 4 significant figures. This one also I can have 4 sig figs, which mean in this case 4 decimal place, since it is small numbers. And because of that, all the rest I can have 4 significant figures always. Okay. Let's do first calculation like we done earlier. And you know the length correction too. Let's take a look at that again. If you click on the show results, it will tell you what the end correction should be. So we'll use that there suggested end correction. Then I should add about 0.015 equal sign 4 times the length should be the wavelength. We need 1/, wavelength. The reason later we're going to be planning on making a graph, right? So we need 1/, wavelength. And we need the speed of the sound equal sign frequency times the wavelength. Now you can see this number is large. The reason I'm on the second resonance mode, right? So I have to consider that second resonance mode. When you do lambda, so you have to make sure I consider second resonance mode, which means if you go to page number 1, lambda is 4L/N, right? So I have to do that carefully. Earlier N was 1, now N is 2, which means I have to divide this by 2. So this whole thing divided by 2. Still much larger compared to the previous. So the error is actually too high. Let's see why the error is too high. Which mean only reason may be, oh, I know why. Yeah. So you have to be careful now. The second resonance mode, N is actually 3, not 2. Okay, sorry. Yep. This should be 3. Then we are good. keep the n correction and then make sure n is actually 3 now. Okay, let me write it down here too. So let me write it down that also here too, that will be useful. Now in this case, we are using first resonance, which means n equal 1. And then here table 2, we are using second resonance, small n is actually 3. Okay, so it's actually a little bit of more error than previously, even considering the n correction, but that's okay. We divide by 3, okay, not 2, because n number 2, second resonance is actually number 3 now, okay, because we're going to have only odd number of 1/4 loops. First one is 1/4 of the loop. That's the first resonance. Then the second one is actually 3 of 1/4 loops, right? So which means that is 3 lambda divided by 4. And then next one is 5 lambda divided by 4. Next one is 7 lambda divided by 4, and then so on. So we have only odd numbers here. Okay, question. Okay, no question. Then let's continue. Let's take a look at the second one then. It's the same thing now, okay? There's no difference. You know how to do the one calculation, then finish the data set. Then the calculation is much easier. You highlight this whole area and then click and drag. It will do the calculation for you. Okay? That much easier. Let's do 350. It's the same, you know, same exact measurement, right? I need 350. 350. And then let's bring this whole thing back again all the way to the lowest point, and then sound on, and then slowly bring it up. The tube length, you have to wait until you hear the first resonance. Sound is switch off, actually switch on. That's the first, that was the first resonance. Okay, then continue upward more and more. That's the second resonance. Okay, when you get the second resonance, let's measure the, when you get the second resonance, let's measure the length. So now the length is about 70.1. So which means I'm on now 350, 70.1 mean 0.7010, right? 70.1. Rest of the calculation you can highlight all three and then do very easily. And only thing I need to make sure the number of significant figures, highlight all. Format cells, I can go 1 number and 3 decimal places to get 4 sig figs. And then this one also I need 4 sig figs. 3 decimal place plus 1 number, 4 sig figs. And this one also I need 4 sig figs. 3 numbers and then 1 decimal place is fine there. With this first one you can see I don't have 4 sig fig. You can reformat cell by cell if that happens. Okay, all you have to go into that cell, format cell, and then I can add extra decimal place. Then I have 4 sig fig there. Okay, question. No question? Anybody have any question? Okay, then let's continue. Oh, in correction we need to do here actually, yeah, for everyone. So easiest way to do that is we can do n correction when we do lambda calculation, then it will automatically take care of. You can do that way actually, since it is the same number. When you do lambda calculation, let's do the n correction here. Parentheses C26 plus 0.015. Then I don't need to add it again and again. When I do that calculation, automatically it will take care of the n correction. Okay, so what I did, instead of adding to L here, I did that when I do the lambda calculation here. See that? C26 plus 0.015. Then when I do the later calculation, I'm going to click and drag. Then I don't need to rewrite again and again that number here. But you can do either way you like, right? Previously we done with this line. And now I'm doing that for another different option. Okay, but it's okay to do it here the same way we done earlier. Nothing wrong. Just do it the way it is easier for you. That's fine. Okay, question. Okay, then let's continue. It's the same kind of measurement. Now you know how to do it. I need next one 350, next one is 400. 400. Then let's go back and then bring the tube all the way to the starting point. Click the sound on and then slowly increase. That was the first resonance. Continue increasing the length. That's the second. When you reach the second, then we'll measure it. 61.3. So that means this is 0.613. Now this one should be 400. Let's check the calculation. Yeah, that's almost about the same numbers. I have a little bit of error compared to previous, about maybe 5%, but that's okay. All right, question. Let's do then 450. We're going to bring back this all the way to the starting point. And 450. 450, sound on. And then bring this up. First one, continuously go up. Second one, sound off. Measure the length, 54.4. 0.544. This is 450. And if I do the calculation, it's about the same. This one behaves very same. Compared to previously, we had actually slightly go high and then lower values, but compared to that, this is actually very consistent, all the numbers. Question. Error correction applied to here. When I do the lambda calculation, it applied. So because of that, all the calculation when I do here, it will automatically take care of. But you can apply into here, nothing wrong, but don't apply it twice, okay? If you apply into the both, then it's going to be incorrect. Apply into one. If you want to apply, just do it here or do it on the lambda. C29, we did not that because it applied into here. It applied into here. It applied into lambda now. Because of that, when you do the calculation, all of these, it automatically take care of that. See that? Okay, any other question? Okay, then let's do next one. 450, 500, 500. Let's bring this back and sound on. Bring it up slowly. First one, then continuously go up. Second one, sound off. Measure it 48.482. Now we are on 500. And last one, 550. Bring this back. 550. 550. Sound on. Bring this up. First one, continuously go up. The second one. Sound off. Measure it. 43.8.438. Now we're doing 550. Okay, so then let's go back to the lab manual and then take a look what question it asking for the case number 2. Okay, let's go to lab manual and then take a look what it's asking on there. Okay, case 2, part B. We are on second resonance. It's the same thing actually. There's nothing new to do there. Second resonance is also asking you the same thing. Do the temperature correction for the speed of the sound, and then calculate the average. Then compare that with the expected, and then do a graph. Compare with the graph value. Okay. So let's do that. It's very simple. You know exactly what to do, right? So expected value doesn't change at all. Okay, you can use these numbers as it is. I'm gonna copy all of these. Actually, all of these into here, then I can use exactly same thing again. Okay, now let's see, expected value remains the same. And when I do PE, I need this PE actually we don't need, sorry, you don't need that number. Technically, we know we need only average value. Let's do the average. Same function, I actually copy paste from previous, but you can rewrite the function if you're new to this kind of work. But if you know what you're doing, then you can copy paste the previous functions, okay, directly. Then these two I need to do actually, okay, these two are not correct. Now this is the average. Let's see, average versus expected. Average versus expected. Let's do that calculation. Equal sign, ABS, parentheses, expected minus average, close bracket, divide by expected, multiplied by 100, 3.65 is still okay. And to get the graph value, I have to do a graph first, right? Okay, question? Let's make a graph again. So I would like to do this way, put the empty graph first, insert, scatter graph, and then let's add the data afterward. So double click on the graph, select data, add data. X should be now 1 over lambda, and Y should be now frequency, and then click OK, again. We have data set is very consistent other than the previous one. You can see very nice linear data set. And you need all these, okay? Make sure you add the chart title, and then you add the axis title. I'm not going to do that again, but you have to do them, okay? And all of those has a little bit of point. If anything missing, they are going to be point reduction. And we need the trend line again. Trend line, I need linear. And then double click on the trend line, options, trend line. And then I need all these three. I can extrapolate to see whether the trend line is actually going through 0, 0. If you extrapolate that, you can see that dash line, dotted line should actually cross through 0, 0 point, okay? And graph value is 33308. Let's do this percentage error. Equal sign ABS, parentheses, expected 345 minus graph value 333.08, close brackets, divide by expected, multiply by 100. About 3.6% error, still not bad. Okay, question. Any question? Start title, frequency versus 1 over lambda, 1 over wavelength, and then x-axis, 1 over wavelength, 1 over meters unit, and then y-axis is frequency. Frequency unit hertz, that is actually 1 over second. Okay, you can do either way, hertz or 1 over second. Doesn't matter, both are correct. Okay, question. No questions? All right, so we have to do 2 more tables. Those are not really difficult at all. The third table is actually, we're going to take a look the temperature effect, and the fourth table is we're going to take a look the effect of the medium. So technically there's no graph or anything for those two. We're going to take a look what's the temperature effect, whether really the sound speed is changing as a function of temperature or not. Okay, that's what we're going to do there. And next one is the effect of the medium. So let's take a quick break, and then we'll start in 10 minutes. 140. After we finish this one, let's take a look couple of questions from last 2 chapters, okay, and also discuss a little bit about the exam number 1 next week. Okay, if you have any question, please ask, okay. Let me check the question. Doing the data sheet is up to you, right? So the whole idea is that I do a whole experiment. The idea is that you can do the experiment with me together. But if you want to do it later, I don't know, then you're just wasting a lot of time. Just during the experiment time, there's nothing much to do otherwise. Just watching just how the experiment is done, not going to help you. So the only best approach is that watch how we do the experiment and then do it yourself. Then you can learn that better. Okay, so let's continue. So let's take a look what is the effect of the, anybody have any other question? Let's take a look at the sound speed, how it changes as a function of temperature, right? So to do that, we can basically, now that part is impossible to do in class, right? So that's why this simulation actually sometimes is good in one way, because we can test some of the stuff we cannot do in class. And in some way, it really not much useful because we can't really gain the experience of hand-on experience. Like, for example, the first two, if you do this in class, it's gonna take the whole class time because they're getting all the setup done and then finding that resonance point. Those are very time consuming things to do. Now with the simulator, it's just like extremely simple. So I even went really super slowly today, and then still we have a lot of time. So it's really easy. So let's continue. This part is something we can't do in the lab, but we can test here. We can use the first resonance mode, but we can ask purposely, keeping the different temperature in our simulator, and then we'll take a look whether or how the speed of the sound varies. Okay, so that's the plan. So all we have to do, let's say how many number of, I can go 2, 25, 50, 75, 95, 25 we done earlier. Let's do something different number here. Maybe I can do 30 there, okay? 30, 50, 75, 95. Let's start at 2 degrees Celsius. 2 degrees Celsius. And then keep the up. And then let's do the first resonance. Diameter don't change at all. Then the resonance, to take that, maybe we can go back to 300 frequency. Let's write it down, those information too. We actually need them when you do the calculation, right? Let's do here, we do in medium air, and then we do in tube diameter, doesn't matter. We're not going to change that all. The frequency if we do in about 300 hertz, okay? 300.0. Then we have that 4 significant figures there, 300 hertz. And then we're studying first resonance only here, okay? Only considering first resonance. Okay, so those information we need, just I add on top of that table. Length we're going to measure in unit meters, and then because of that lambda going to be unit meters, and the speed of the sound we can calculate. That's going to be unit of meter per second. Okay, all you have to do, bring this back all the way to the lowest length, and then make the sound on, and then bring it up slowly. That's the first resonance mode, okay? And also earlier, I forgot to mention you that every time you do a simulator, you have to get the picture, right? Because you have to do the procedure section. In the procedure section, you have to add pictures as needed, okay? This one, technically, only one pictures you need. Let's take a screenshot. And then I'm gonna add that screenshot also here, because later you can actually use that. But for the datasheet purposes, it's not required, but I'm going to add it anyway. Because if you do that as a practice, that will be a little bit easier. So let's add a screenshot. To add the screenshot, insert pictures, and click the down arrow. You will see how to select the pictures and then add it. And then get rid of all the background, which you don't like to have there. You can crop right-hand side, very top. Click on the crop, and then I need only to see the simulator part, right? So just crop out all the unnecessary parts. Okay, and then click the crop again. So that's our picture. If you have a picture anywhere on your lab report, make sure that should be renamed. Okay, so the pictures are renamed as figures. If this is figure 1, this is the schematic diagram of sound wave experiment, or you can say sound wave simulator. Okay, so you need to make sure you rename accordingly. Okay. All right, question. Now, if you complete everything on the Excel sheet after you've done the class, technically you have all the stuff you need whenever then you get the time. Then you just need to put it all together into your Word file. That's all. Then theory part also for this lab is not really long. It just two equation, and then you have to explain. Okay, you can't just put the equation only. Just write it down, little bit of explanation, what the resonance mode, things like that. Then procedure you can do bullet form, and then the discussion only you can do little bit detail. Okay, so let's continue. So any question? We are on the resonance point. Let's measure that. Exactly 25. So length is 25 mean 0.25. And then let's format this. I can go for sig fig, right? Number. I can go for decimal places to represent for sig fig, measuring in the meter ruler. Then the lambda gonna be, you know, now I have to do that correction too, right? Equal sign 4 times parentheses L plus 0.015 with that correction. Okay, and also reformat this also into about 4 sig figs. And then let's calculate the V equals sign lambda times F. Now the frequency is 300 times lambda I just calculated. 318. Now let's check that expected value. Let's add another column here to see the expected value. Okay. So let me reformat that little bit. That's better to have it actually check with our expected result. Let's do expected value. You know how to do the temperature correction. Equal sign. We expecting 331 at 0 degree. Now this is at 2 degree, right? So which means 331 times 331 also not the exact number. It is a rounded value. Okay, and it's QRT and parentheses, another parentheses, 273 plus the degree value is right here, close brackets, divide by 273, close brackets. So we expecting about like 332, but we getting about like 318. That's okay. Let's do the percentage error to see how much is off. Percentage error equal sign ABS, parentheses, expected minus calculated, divide by expected, F39, divide by expected, F39, multiply by 100. About like 4% error. Let me copy paste those two functions here, okay? So that's again for the temperature correction. Temperature correction. And then this one is actually for the percentage error. Percentage error. Okay, those two for table number 3, okay? And let us make this table a little bit extended now. This is actually expected value. We can say we expected unit is meter per second with the temperature correction, and then this is PE between them, okay? And then there's no unit, it's a percentage sign. All right, question. Okay, then let's continue this measurement then. So all we have to do now, you know what to do. All we're going to do, increase the temperature slowly. Let's do 30 degrees C. 30 degrees C. Bring back this into the starting point. Sound on, and then let's bring it up. Okay, that's the first, we are studying only first resonance. Okay, first resonance 28.8. Let's take a look at that again. 28.8. 0.288, and then let's do all of these calculation at single step. So that's the advantage, right? If you're doing this with the calculator, you have to do this again and highlight all and then do all the calculation together. So it's very simple, and only thing I had to take care of number of sig figs here should be 4, 3 numbers plus 1 decimal, and number of sig figs here also should be about 4. There's no meaning anything more than that.
Professor,
Yeah, what's up?
how do you do that again? Like get the calculations without typing it in?
Oh, you have to do this. I complete this whole first row, right? See this one, first row, everything I did. So then if you want to do the same downward direction on the column direction, all you have to do, highlight that all 4. And then very end, you see green solid dot. Just click on that and then drag downward direction. You can do one cell by cell at a time, or you can do all 4 at same time. Okay, question. Let's do 50 degree. 50 degree. Bring it back, starting to all the way to starting point. Sound on, and then bring it up. Sound off. Measure that number, 29.4. 0.294. And then let's do 75. 75, sound on. Bring the tube up. Sound off. Measure the length. 75 also 29.4. I think I did a mistake at 50. Let's go back there. Seems to be not changing at all. Check the 50 again very quickly. Seems to be length doesn't change at all then. Everything looks good. Sound on, and then bring it up. Yeah. Twenty-eight two. Let's go back. I want to check the other one too. What's the other one I did? 30 degree. Check that too very quickly. Let's check that too very quickly. Sound on. Bring this up. Seems to be. I'm going to read when I hear the first time, okay, the noise, because it seems to be if I go a little bit higher, because the length change looks very, very small from here. If I go a little bit higher, it seems to be almost I'm going to repeat the same number. So let me redo this all the way from the 2 to make sure everything is fine, okay? First time when you hear the noise, I'm going to stop the length and then stop and measure the length, okay? Sound on. Yeah, that should be fine. First one should be fine, nothing to worry. Let's check the second one, 25 or 30. Sound on and bring it up. You have to go very slowly here. Actually, it's changing a lot. If you have a small movement there, it seems to be it's changed a lot. Maybe even 27 is the same sound. Okay, I'm gonna take it to 26.9.269. Let's see my error. Yeah, so my error is actually decreasing, which means it should be less than my previous number. Okay. Yeah, you have to read that again. Okay, 30, and then I'm reading now 50. Sound should be on. You have to move very slowly because the length difference now is extremely small. Okay, with the temperature. 26.9. That's much higher than the previous. But you can see even in between 27 and 28, it looked like about the same noise. Okay. So okay, so one way to do that, because it seems to be very sensitive there. One way to do that, click on this length change slider here, and then do add the arrow. Then try to find the best position. Best position means the intensity maximum point. Okay. If you click and drag, unlike the previous case, our error seems to be very high here. Okay. So let's do this way. Sound on, and then I'm going to use this slider here. Okay, for the length. Sound on. Click on here. You can see the sound is starting about like 26.9 previous point. See, even before the previous point, now it is increasing. And it's the same, about the same sound all the way to like 27 to 29. So that will be a problem when you're reading, right? It looks about the same sound from like 27 point something all the way to like 28.5 or so. So let's read the first starting point of the maximum sound. Okay. Let's go back. Twenty-seven to maybe 5. Yeah, let's read that 27.5. 275, and then let's check the error. How much error is that? If the error is lower, that's better. Yeah, 3.3%. And then you do 2 other points. Okay, now this is 50. I need 75 and 95, because you can see the temperature correction equation. It's in Kelvin. Room temperature divided by 273 square root of that. It is very small change from one point to another, right? Because of that, length change is actually very small. The error happening there are going to be extremely sensitive. So let's do 75. Any question so far? 75, sound on. Again, I'm going to use the slider here, okay? When I see first maximum noise, I'm going to read that number, 0.284. Let's do that. Check quickly whether that's reasonable answer. Yeah, error within the margin of 4%. We expected is the temperature correction here we do, right? Right here. Should be temperature correction, that is the we expected. V parentheses expected means actually with the temperature correction. Okay. And the last one I need to do is the 95 all the way to the end of the temperature, and then sound on. I'm going to use this slider. The 30.0.3. Let's check that calculation. Yeah, so that's 1.6% of error. So that's good. Okay, so question. Good, no question. Okay, then let's take a look at the last one. And the last table, what we're going to take a look, the effect of the medium, right? Gas type, whether the sound velocity is really changing if we change the type of the gas. And then let's take a look. That also very difficult to do if we do this in-person setting. So that's the advantage in these simulations. We can actually test some of the stuff we really can't do in-person setting in our lab. But if you have a really good research lab, you can actually do these things in research labs. Okay. Let's take a look. Type of the gas. There's no unit for that. We don't need the units there. Length we will be measuring again in meters. Lambda we will be measuring again in meters. And then sound speed gonna be in unit of meter per second. Now with the gas type, I can't really do any other calculation here. We basically checking what will be the sound speed, whether it is changing or not. Okay, and the couple of other information you can add here. Maybe for example, we would like to have the frequency, those things, right? So we will be doing temperature. Let's do at room temperature, right? So temperature, let's say about 25 degrees C, and then frequency, let's do at 300 Hertz, okay? So I just add this line right here, okay? And AR we already done, right? So all the previous calculation for the AR. I think other than AR, we can select 5 more different stuff. So let's select carbon dioxide, and then we're going to do temperature at room temperature about like 25 degrees C. Tube diameter, leave it like that. Frequency, leave it like that. And let's type here carbon dioxide. Carbon dioxide. And let's bring this back all the way to the smallest length, and then sound on, and then slowly bring it up. You can actually use the slider. Okay, it seems to be more accurate if you're doing it from here. Maybe about like 20.2. I can read this to 4 decimal places. Numbers, 4 decimal places for the accuracy. Lambda going to be equal sign. Length value, 4 times. We're still doing the first resonance mode. Okay, please add that also into here. You need those when you do the discussion part, right? We're doing the first resonance mode, because of that lambda is equal 4 times parentheses length, but I have to do the length correction, which means I have to add 0.015. And let's calculate the sound expected, equal sign, and the sound calculated. Frequency is 300 times the wavelength 0.86. So now it's a very different value, but we can't compare that number now to anything because the medium is completely different, right? So if you want to do that, we have to have the other information like what's the bulk modulus or the density of that medium and then so on, okay? This one also I can have 4 sig figs, which means 4 decimals here. And this one also I can have 4 sig fig, 3 numbers plus 1 decimal. Okay, question. Everybody get that idea? Any question? All right, then let's continue. It's a very simple calculation, nothing really much to do there. We're just observing that behavior, right? So all we have to do, change that into nitrogen. Let's do the same, sound on. Maybe 27.4. So now we're doing nitrogen, okay? Nitrogen about 0.274, and then these two you can calculate easily. And then so on. So let's do other three. We can do oxygen, sound on. $25.7. Oxygen 0.257. And then these two you can just click and drag that right hand side, very bottom. There's a green dot if you click on any cell. If you click and drag downward, it will do the calculation for you, right? So the next two, argon and then chlorine. Let's do argon. Sound on. $25.2. 0.252. And the last one is chlorine. Sound on. $16.4. Chlorine 0.164, and then these two calculations you can do easily by just click and drag that green color dot. Now you can see with the gases, carbon dioxide is much lower than the expected value. Nitrogen is very close. You can see because why? Our regular atmosphere about 70% nitrogen, right? So we expecting it to be about the same number as we expecting. So our real number we expecting in the air about 340 something, right? So that's good match to our room temperature value. And when it go to carbon dioxide, less. And the oxygen is only slightly less because our atmosphere has a lot of oxygen too, right? And the argon is actually close to oxygen, but I don't know the reason exactly. Maybe the properties of oxygen and argon. Our atmosphere doesn't have a lot of argon. So that argon is not really readily available, I think. And the chlorine also